axis or water balance relationship along the elevation gradient, we can find different runoff coefficient along elevation. And the higher elevation, the higher runoff coefficient and higher elevation indicates that greater portion of the rain end up as runoff in higher elevation. That is to say, different vegetation types can lead to various precipitation redistribution pattern and runoff generation mechanisms. And those discrepancies in runoff generation mechanisms can be linked to subsurface properties, such as subsurface layering patterns, soil microstructures, and soil hydraulic properties. And the studies in our study site in the Gunga Mountain, subsurface flow is very sensitive to rainfall input, and subsurface flow dominates the flow regimes after rainfall. And because of the presence of the root soil rock complex structure, the threshold value of the precipitation amount to trigger subsurface storm flow can vary significantly. Speaking of subsurface structure, we come to challenge 2. That is how to link subsurface structures to water flux or water storage in forest ecosystems. In traditional hydrological modeling, hydrologists often treat subsurface as a black box without fully considering the heterogeneity of subsurface. However, the hidden half of the creek zone is characterized by subsurface structural heterogeneity, and such heterogeneity influences the coevolution of soil formation, hydrological processes, and biodiversity. Another limitation in current ecohydrological research is the lack of proper perspective or paradigm to deal with the medium number system. The medium number system is characterized by organized complexity. That is to say, both analytical treatment or statistical approaches can be ineffective for the medium number system. Therefore, we propose a 4M approach, including mapping, modeling, monitoring, and managing to deal with medium number system. In such a way, the form, process, and functions of the ecohydrological components can be interlinked. And speaking of imaging the subsurface, geophysical imaging technologies provide a new opportunity for us to visualize the structure, the process in the subsurface. And these figures are examples of subsurface structures resulted from electrical resistivity tomography, seismic methods, and ground penetration radar, and surface soil salinity mapped by electromagnetic induction. And our group has used different geophysics tools to map subsurface ecohydrological structures. For example, here shows the application of ground penetrating radar to identify and map routes and reconstruct root system struct architecture which matches reasonably with ground truth. And we have also enhanced the ground penetrating radar-based root detection methods in several ways, and after the enhancement, we can have a better root detection efficiency. And with a better characterization of the root zone, of the root distribution, we can find some interesting patterns of lateral root distribution. Like shown here, more roots are distributing at the midpoint between the neighboring plants. And we infer that is the result of the interplant competition for water and other resources in the subsurface. And based on these enhanced scales, we try to look at the relationship between root distribution and soil water distribution. And on the vertical direction, we find those two factors are positively related. That is, the higher the water content, the more abundant the roots. But on the other hand, on the horizontal direction, such a relationship is totally different. As you can see, at most root zone depths, such relationship is negative. That means the more the roots, the less the soil water content. So the soil, water, and root relationship in the subsurface is anisotropic at different directions. And also, we use the signal differences on ground penetrating radar images before and after rainfall infiltration. We can identify hotspots of soil water change, and based on this information, we can reconstruct subsurface lateral flow path. And couple that method with electrical resistivity tomography, we successfully track the flow path after the stain flow infiltrates into the soil. And we confirm that after the stain flow infiltrates into the soil, part of the water can flow along lateral roots. And those results are later validated by field excavation. And this understanding helps us to further enhance the double funneling model that describes rainfall redistribution by vegetation, especially for the subsurface part. And for the remaining slides, I'd like to briefly talk about sustainable management of forest ecosystems under human disturbances, especially how to search for an optimal forest cover that can foster sustainable development. And you can see from this figure, as forest cover increases, different functions of forest shows different trends. For example, at the field scale, with increasing forest cover, the water yield capacity decrease, but wood production and carbon sequestration capacity increase. And other, like hill slope scale and regional scale, greening also significantly influence the water cycling processes. Okay, we're trying to answer, is there also a best forest cover for flood control? Flood control is an important function for water regulation. We firstly integrate storm flow, subsurface flow module into traditional distributed hydrological model. By considering the subsurface flow processes, we can better represent the hill slope hydrological processes, and we run the model in different typical catchments, mountain catchments in southwest China. And here's what we found. The vertical axis is the flood control capacity, which is measured by the rainfall threshold. And we can find the rainfall threshold increase, but non-linearly, with growing forest cover, especially when the forest cover reaches 70%. After 70%, there is a sudden jump. And in addition to that general trend, we also found that the flood control capacity is also controlled by antecedent soil, like the catchment water condition, water holding capacity of the soil, and other factors like watershed features. And we will also examine the possible mechanisms of water yield change after greening in Chinese Loess Plateau. This is another river basin. In addition to Yangtze River Basin, the second largest river basin in China is the Yellow River Basin. And during the past decades, as you can see from the figures, the Chinese Loess Plateau has experienced an evident greening trend. And at the same time, the mean annual temperature and the mean annual temperature shows a slightly increased trend with the mean annual precipitation staying relatively stable. But during that time, both the annual runoff and sediment load in the Yellow River, you can see, decreased significantly. To try to explore the linkage between greening and reduced runoff and sediment load, we chose a paired catchment on the Chinese Loess Plateau. One of the paired catchment experiences natural revegetation for like 50 or 60 years. So the landscape is like a grassland catchment, and the other catchment has undergone strong human activities, especially reforestation. And now you can see that catchment displays a forest catchment landscape. And the color of the circles on the right indicating the maximum wetting depth in the soil after each rainfall event, and red indicating deeper. So you can see here different catchment, different slope position has significant control of the maximum wetting depth. And at the same help slope position, forest land facilitates deep percolation. So more water can go to the deep soil. And also we find terrain and vegetation type together determine the runoff coefficient, and the runoff coefficient varies significantly across the sites. And for stream flow generation, we find that compared to the grassland, indicating by the middle panel with the red curves, the blue lines in below, that is the results of the forest catchment. You can see the flow generation is much lower than the grassland catchment. So we see that reforestation on the headwater catchment on Chinese Loess Plateau has restricted stream flow generation. Only during several strong storm events can we observe stream generation in the valley, in the forest catchment. And this is the result of the wavefront velocity. It measures how fast the water goes through the soil matrix. And the color indicates and the size of the circle indicates the velocity. And left is the results of the grassland catchment, and right is the results of the forest catchment. And it is evident that forest land shows faster wavefront velocity. And the faster waving velocity can also be influenced by the peak intensity of the precipitation and other rainfall characteristics. So, based on those events, we try to link greening and the water yield capacity. And here's some take-home messages of our today's talk. Challenge 1, the relationship between vegetation change and water yield is not linear and can be spatially various. For challenge 2, the new advancement in technology help us to better understand of the form and function relationship of water cycling through the Great Zone. For challenge 3, reforestation or other vegetation rehabilitation measures has different impact on water-related functions of forested ecosystems. So we have to be carefully to choose the proper strategy for reforestation. Okay, here's some information for both Dr. Wang and myself. And thank you, and I wish a big success of this workshop, and you all have a good time in Chongqing. Thank you.